Hello students, welcome to new lesson 8.1 Introduction to Vectors. In this lesson we are going to learn how to identify vector quantities, how to represent a vector geometrically, and how to operate with vectors also geometrically. In this video we are going to discuss the first two objectives, and I'll leave the third one for another video. Okay, so identifying vector quantities. Maybe you're familiar with this concept, vectors, from the physics class. Many physical quantities such as speed can be completely described by a single number called a scalar. This number indicates the magnitude or size of the quantity. So usually scalar quantities are described by magnitude only, whereas a vector is a quantity that has both magnitude and direction, such as the velocity. The velocity of a football is a vector that describes both the speed and the direction of the ball. Force is also another example of vector quantity. It needs magnitude and direction to be completely described, and so many other examples. Okay, let's take a few examples to see which are scalars and which are vectors. For example, here, a boat traveling 15 miles per hour. So this quantity is described by a number here, 15 miles only. No direction is mentioned. So this quantity here is a scalar quantity. A hiker walking 25 steps due west. So 25 steps, this is magnitude. Due west, this is direction. So magnitude plus direction is vector quantity. A person's weight on a bathroom scale. Here, you should all know that weight is a type of force, and force is a vector quantity. Simply, weight is force because it's the product of m times g, and g is the pull of gravity. Gravity it has a magnitude, which is 9.8, and direction, which is downward, so weight is also a vector. Here are other three examples. I leave them for you to do them. Okay. So this is for identifying vector quantities, or differentiating between vector and scalar quantities. Second part is how to represent vectors geometrically. First, a vector can be represented geometrically by a directed line segment or arrow diagram, as you see here. This arrow diagram shows both magnitude and direction. Now, if I consider this line segment, has initial point here, the point where this arrow starts from, and it's called the initial point. And it is also called tail of this arrow. And here the tip of the arrow is called the terminal point, where this arrow ends or stops. It is also called the head or the tail. Okay? Now, if this point is, let's say, A, and this point is B, then this arrow here represents a vector which I can call AB. Or, if this segment is A, then this arrow, or this is a vector whose name is A also. Now, if this vector has its initial point at the origin of a coordinate system, if I drag this arrow to the origin here of this coordinate system xy, then we say that this vector is in standard position. So this is the standard position. The direction of this arrow is the angle between this vector and the horizontal line. Now, this horizontal line can be represented by the positive side of the x-axis. Okay, so therefore the direction of this vector is determined by this angle, the angle that this vector makes with the positive x-axis. Let's say it's 35 degrees. So I can say here, and still this is vector A or AB. The direction of A with an arrow on its top, always, all vector quantities, whenever you write a vector quantity, you should not forget to put this arrow on the top. Okay, the direction of A is 35 degrees. So this is one way to describe the direction of a vector when it is in standard position. Okay, now as for the magnitude, remember vectors have direction and magnitude. The length of the line segment represents the magnitude, and the longer this line segment is, the greater the magnitude, and vice versa. All right? Okay, so how can I figure out the magnitude of this arrow here? To do so, we need to set a scale here. If I assume that this vector represents a velocity quantity, okay, so it's in meters per second, and I take the scale that every 1 centimeter I draw on the paper represents let's say 5 meters per second. Alright, so based on this scale, what is the magnitude of this vector? Here I have to draw or to measure the length of this arrow to know how many centimeters. When I know how many centimeters, from the scale I can figure out what's the magnitude of vector A. So I'll grab a ruler. I put it at the 0. This ruler is graduate in centimeters. So it's 1, 2, 3, 4 centimeters. So if this arrow is 4 centimeters, how many meters per second are they? I guess you know how to use this method. You can crisscross. This times this and this times this. This times this is equal to this times this. So 1 times x is equal to 4 times 5 is 20, and the unit is meter per second. So here, the magnitude of A is equal to 20 meter per second, or this can be written in a different way. A vector in absolute values. This means that we are talking about the magnitude of A equal to 20 meter per second. Okay, now we talked about the direction here when the vector is in standard form, but the vector could be in, or could not be, or could be in any other position other than the standard position. So how can we define the direction then? So here we have two other ways to describe the direction. The direction of a vector can also be given as a bearing. Okay, quadrant bearing number 1 and true bearing number 2. Let's see what does each one mean. A quadrant bearing phi, it's represented by the symbol phi, a Greek symbol, is a directional measurement, is a measurement for the direction, and this phi is always between 0 and 90 degrees. 0 and 90 degrees east or west of the north-south line. So this is the north-south line. The directions here are north, east, south, west. You can remember them as never eat shredded wheat. Alright, so I have this reference line here, north-south, and either I am like to this side of north or to this side of north, or I am to this side of south or to this side of south. Okay, so that's why it's always between 0 and 90 degrees. For example, for this arrow here, for this vector v, the quadrant bearing of v is 50 degrees east of south. So I'm 50 degrees away from south toward east, or we call it southeast, and written as 50 degrees east of south. Okay, so first comes S, then E. If I have another vector, let's say a vector that is over here. Now the quadrant bearing here is the angle here from north. Okay, let's say it's like 65 degrees. So we say that this arrow has a quadrant bearing of 65 degrees east of north. So east of north. Okay. One more. This arrow here has an angle, let's say, of 20 degrees. So the quadrant bearing of this vector is 20 degrees west of north. All right? Okay, so this is for the quadrant bearing. Now for the true bearing, sorry, a true bearing is a directional measurement as well, where the angle now is measured clockwise in this direction from north. So never eat shredded wheat. From north we go clockwise. True bearings are always given using 3 digits. So a direction that measures 25 degrees clockwise from north would be written as a true bearing of 0 to 5, 3 digits. Okay? So it's from here to this vector, it's 25 degrees, but the true bearing is written as 0 to 25. Let's say for this arrow here, for this vector, what's the true bearing for this vector? To find the true bearing, we need to know the angle from north clockwise all the way down to this arrow. This is like kind of 210, let's say. So the true bearing of this vector is 210, 3 digits. Okay, so the true bearing, 3 digits. The quadrant bearing is between 0 and 90, so it's always 2 digits. Okay, so those are for the 3 ways to describe the direction of a vector. Let's take examples, see how we represent vectors geometrically. Okay, so use a ruler and a protractor to draw an arrow diagram for each quantity described. Include a scale on each diagram. The scale is very important here in order to draw the arrow. So, part A, I have vector A. Always, whenever we are working with vectors, we need to put the arrow above the letter here. Equal 20 feet per second at a bearing of 0, 30 or 30 degrees. So is this a quadrant bearing or a true bearing? Because I have 3 digits here, so it's a true bearing direction. So I'm measuring it from north. This is north. This is east. Never eat shredded wheat. Okay, so I have to go from north clockwise 30 degrees. So I get my protractor. I put the 0 on the north. This is the 0 up. The 0 is here. Now I go 30 degrees from here. 10, 20, and 30 degrees. I'll just mark a point here for 30-degree angle. Then I remove this. Now, before I draw the arrow, I need to know how long this arrow should be. And to know how long this arrow should be, I need to use a scale, because here A is 20 feet per second. I cannot draw 20 feet per second here. I can draw like number of centimeters, 2 centimeters, 3 centimeters, 4 centimeters, etc. So that's why I need to set a scale. And the scale that I have to choose has to be a convenient one. Let's say scale of 1 centimeter corresponds to maybe 5 feet per second. This is a convenient scale. But if I choose like 1 centimeter corresponds to 1 feet per second, I would end up with a 20 centimeter arrow. 20 centimeter is very long to fit in this piece of paper. So 1 centimeter, 5 feet per second is a convenient one. So if I have 20 feet per second, how many centimeters this should be drawn. Again, the crisscross, x times 5 equal to 1 times 20. So 5x equal 20, x equal 20 over 5, so x is equal to 4 centimeter. So now I know that the arrow should be 4 centimeters starting from the origin. So I get the ruler, put it at the 0, and I have to align the ruler along with this point. Okay, oh my god, undo. So here's 0. Alright, so now I draw 4 centimeters. Just change the color. And here is 4. And this is vector A. And the angle here is 30 degrees. Okay? Another example. V, again, equals 75 pounds of force at 140 degrees to the horizontal. So 140 degrees to the horizontal means that I'm talking about a vector that is in standard position. So 140 degrees from the positive x-axis. Okay, so first I mark my 140 degree angle. I have to turn this to make the 0 along the positive x-axis. Okay, here we go. 140 degrees is over here. You just need to mark a point. Now, how long this arrow should be? I need to use the scale. 1 centimeter corresponds to 75 pounds. I can take 1 centimeter as equal or corresponds to 25 pounds. So the 75 pounds, how many centimeters do you think would that be equal to? X equal, or x times 25 equal to 75 times 1 over 25 over 25. So x is equal to 75 over 25, and that is 3 centimeters. Okay, so the 0 over the origin, and okay, and here I go 3 centimeters. Yes, okay, and this is vector V. This angle here is 140 degrees. Okay, for the third one, 30 miles per hour at a bearing of S 6 degrees west. Now this bearing here is a quadrant bearing. Okay, so I will just grab this here, the directions. Okay, so 60 degrees, this is how it's read, 60 degrees west of south. Okay, so if I am at south here, south, I have to go 60 degrees toward west. From here I go 60 degrees toward west. This is west. Okay, so 60 degrees is over here. I have to put the protractor along south, 0 degrees along south. And I go 60 degrees. 60 degrees is over here. Okay, now 30 miles, again scale, 1 centimeter could be equal to or represent 10 miles per hour. So 30 miles per hour, how many centimeters? X would be 3. You do the math. So I have to draw 3 centimeters. Again, I grab the ruler here. Zero and 3 centimeters. Oh, this is 3 centimeters. And this is vector z. The 60 is here now because it's a quadrant bearing. Okay? Alright, so this is for representing vectors geometrically. I want you at the end to practice those 3 questions. Try to do them. And if you have any questions, after you watch the video, you can write the question you have in the comments, or try to reach me in any way. Okay, thank you for watching this, and see you in the next video. Thank you.